Hello everyone, this is Sopan Chavan and I welcome all the students of BSc third year class, Sri Venkatesh College, Devulgaon Raja. Friends, this is the first lecture on Riemann integral and today we are going to learn some basics which are required for the Riemann integral. So we have the first chapter for this mathematical analysis paper is Riemann integral. So let's go to the Edmodo class. This is the interface for your Edmodo class. Go to the folders. In this folder there is a semester 5 folder. Click on the semester 5 folder. In this semester 5 folder there is a folder called notes. We have given the notes for your chapter Riemann integral. So click on this Riemann integral PDF and let's go to this PDF. This is the chapter first of your mathematical analysis paper. Friends, in this chapter today we are going to learn the geometrical notion of this curve y is equal to f of x and area under this curve and x-axis, and then after that we will learn what is a partition of some closed bounded interval in R. Then we will see what is the length of some intervals, then norm of that partition P, and next we will discuss or what is the refinement for that partition P. So let's start for this first class on the Riemann integral. So let us take one curve y is equal to f of x, which is a non-negative curve. It means that the graph plotted in the xy plane, which is above to the x-axis. So this is y is equal to f of x, the graph for your curve. Friends, the area under this y is equal to f of x and this x-axis is called a capital A, which is the area curve by area between this curve and x-axis. So we know that the definite integrals of f of x. Friends, if you find the integral of f of x for some fixed value under the limits, lower limit and upper limit, then it will give a fixed value to the given integral, and that is called your definite integral of f of x. If you don't have a limits for this integral, then it is an indefinite integral. If we analyze this graph by geometrically, this area A is actually the notions of the area represented by the integral f of x dx. So under this under the limits a to b. So what it means? It means that integration over a to b f of x dx gives some fixed value, and that fixed value will be the area of this A. So now onwards we will learn the definite integrals for we will learn the definite integrals to find the area of some curves. So actually this integration f of x dx, which represents a function which is a derivative of f. If we take the derivative of this integration f of x dx is f. So this definite integral is more fundamental than indefinite integral. Actually this is your indefinite integral, and if you have seen if the limits are given, then it is a definite integral. Now next we will see what is a partition. So let's define the partition. So let's take one closed bounded interval in set of real numbers. So let's take I is equal to closed interval AB, and consider a finite order set x0 comma x1 comma xn. We call this set as P, and actually this set contains a point of this interval I. So it means that the x0 comma x0 x1 and so on xn's are the points of this interval I, and these points have some orders like this. So x0 less than or equal to x1 less than or equal to x2 and so on less than or equal to xn. Then this P is called a partition of this interval I. What is the partition of this interval I? So let's consider any order set, any finite order set for this interval I containing the points of this I, and that element must have order in between them. So like this, then and only then this P is called a partition of interval I. So the partition here, the partition P divides this interval I into subintervals or segments. So let's see how they are. This I1 is equal to close interval x0 comma x1. So this is the first segment of this closed interval AB. So this is the first partition. This is second partition. I2 is your second partition, and so on. This IK close interval xk minus 1 comma xk is your kth subinterval of this I, means the kth partition of this I, and so on. You have n points, so there are n subintervals. There are nth partition of this interval I. So these are the intervals. You can have a different partition of the same interval I, or we can change the points, this x0 comma x1 so on xn. Instead of taking this x0 x1 xn, we can take different, and we partition this interval I into that much interval. So let's illustrate this. Consider the closed bounded interval 1 comma 4, and let's have some partitions of this interval 1 comma 4. P1 is your first partition, P2 is your second partition, and thirds. So these are the partitions, 3 partitions for your closed interval 1 comma 4. In the first partition, we have 2 subintervals. Let's see. We have 3 elements which is in order manner, because 1 is less than or equal to 2, or 2 is less than or equal to 4. And we have partition this closed interval of this real number r into two segments or subintervals. So let's see here 1 to 2 and 2 to 4. So similarly, we have a second partition P2. In this, we have partition this 1 comma 4 to two subintervals or segments. So first segment is your 1 to 2.5 and another is 2.5 to 4. And in we have P3 is your again a partition for this 1 to 4, close interval 1 to 4. So this is like 1 to 2, 2 to 3 and 3 to 4. There are three subinterval or segments. So actually these are the three partitions for this closed interval 1 comma 4. We have an infinite number of partition for this closed interval 1 comma 4. How? So we know that any two real numbers, any two real numbers, there are infinite real numbers. So we can take any partitions or any elements for, to partition this closed interval 1 to 4. So now we will discuss what is the length of given interval. So actually the length of given interval is the difference of last element and first element. So let's denote this delta xk for the length of kth interval, and the length of kth interval is what? Your kth interval is ik, and this is your kth interval xk minus 1 comma xk. And what is the length for this ik? How to find the length for this ik? The length for ik is the difference of last element and first element. It means that xk minus 1. So this is xk minus xk minus 1, and we denote this difference as delta xk, and this is your length for the kth interval. If you have n interval in your hand, and if you find the length of each subinterval, and if you sum these each subinterval, length of each subintervals, then we will get the length of your original, or that original closed bounded interval in R. So let's see here. So you have in hand n k subintervals, and k is equal to 1 to n delta xk, which is equal to, actually this is summation, so we run this k from 1 to n, so we will get delta x1 plus delta x2 plus so on delta xn. But what is delta x1? Your delta x1 is the length for your first interval. Then delta x2 is what? Length for your second interval. This is notation only. So, and this is what? This is delta xn, and this is a length of your nth subinterval or nth interval. So what is the length of delta x1? What is the length for first interval? Your length for first interval is the difference of last element and first element, that is x1 minus x0. So let's put, instead of delta x1, x1 minus x0. Then what is delta x2? Your delta x2 is a length of I2. What is I2? Your I2 is closed interval x1 comma x2, and the length for this I2 is a difference of x2 minus x1. So this is x2 minus x1 and so on. What is the length for nth interval? That is in. That is delta x. Notation is delta xn. So this is xn minus 1. If we add this, we get x1 minus x1 will get cancelled, x2 then minus x2 will get cancelled, and so on. So lastly we will get the only remaining is what? Xn and x minus x naught. So this is xn minus x naught will remain. But what is xn? Your xn is b and your x naught is a. So put here. So this is b minus a. And what is this b minus a? This is the length for ith this is the length for ith interval. So difference of b minus a, difference of b and a. So this is b minus a. So length of I is b minus a. Actually, the sum of length of each subinterval is equal to the length of original interval. Okay. So this is the length of interval. Next, we will see what is norm or mesh of partition P. So this definition is actually the greatest length of segment in the partition P is called norm or mesh of P, and we will denote this norm of P as this notation or by mu of P. So what is the norm of P in mathematical notation? In the mathematical notation, norm of P is equal to maximum of delta x1 comma delta x2 comma so on delta xn. So this is what? This is delta x1 is your length of I1, delta x2 is length of second interval, then second segment I2, and so on. The delta in is nth segment of this interval I. So we have taken the length of each interval and we have taken the maximum of this length. So whatever maximum length of the interval is called the norm or mesh of that partition P. So what is the norm of P? Norm of partition P is the maximum length segment in the what is the norm of P? Norm of P is the maximum length segment. Okay. So let's illustrate this. So we have one partition P1, that is the 1 comma 2 comma 4 for this closed interval 1 to 4, and P2 is another partition for this, and P3 is another partition for this. So we have three partitions for this closed interval 1 to 4. So let's we see what is the norm of P1, what is the norm of P2, and what is the norm of P3. So let's see what is I1. I1 is your first segment 1 to 2, that is closed interval 1 to 2. And what is the length? Length is your delta x1, which is equal to 1, that is 2 minus 1 is 1. What is I2? Your I2 is 2 to 4 closed interval. And what is the length for this I2? That is 4 minus 2, that is 2. So we have two segments for this in this partition for the closed interval 1 to 4. So what is the norm of P? P1. We denote the norm of P1 as mu of P1 or this notation. So mu of P1 is a maximum of this 1 comma 2. What is the maximum for this 2? We have 2 is maximum, that is greater 2 is greater than 1, so maximum is 2. So the mu of P1, that is norm of P1, is 2. Similarly, we have a second partition P2. So first segment is your I1, close interval 1 comma 2.5. So what is the length of this? The length of delta x1, that is length of I1, is your 1.5. 2.5 minus 1 is 1.5. Another segment is your I2, 2.5 to 4. And what is the length of this I2? The length of I2 is 1.5. And what is the maximum of this 1.5 comma 1.5? The maximum is, both are same, so the maximum is 1.5. So the norm of P2 is 1.5. Next, what is the norm of P3? So we have 3 segments for this P3, for this P3, that is I1, I2, I3, and length of I1 is 1, length of I2 is 1, and length of I3 is 1. So all the lengths of the segments are equal, so maximum is same. The maximum is 1 and mu of P3 is 1. So the norm of P3 is 1. Next we will discuss what is refinement. Refinement for the partition P is the set which is bigger than that P, or it contains a P. So the partition P star is called a refinement of P if P star contains P. It means that all the elements of P must be in P star and one element more than that P. Then this P star is called a refinement of P. Now what is common refinement? The common refinement of this, if we have two partitions P1 and P2 for the closed interval AB, then the common refinement for these two partition P1 and P2 is a P star, that is union of P1 and P2. In this union contains a more element than P1 and P2. So this P1 union with P2 is a refinement for P1 as well as P2. Now this is a common refinement. So let's see some examples. P1 is your this 1 comma 2 comma 4, one partition. P2 is another partition. P3 is another partition. Then this P2 is a refinement of this P1 and P3 because all the elements of P1 contains in this P2. Also, all the elements of P3 contains in this P2. So this is this P2 is a refinement for P1 as well as P3. What is the common refinement for P1 and P3? The common refinement for P1 and P3 is P star, which is a 1 comma 2 comma 3 comma 4, which is equal to P star is equal to 1 comma 2 comma 3 comma 4, and this is the refinement for common refinement for your P1 and P3. A refinement of P can be obtained by adjoining the finite number of points to P. Once you have one partition for any interval I, then you can find the refinement for this P. How? we add some elements to this P and we put this set to P star, and this is your refinement for your P. So I hope you understand all these things on this basis of Riemann integral. So I am signing off. Thank you.